Natural language processing inspired by neuroscience. I'm Tonya Hall, and joining me is Sousa Webber, founder and CEO of Cortical.io. Welcome, Francisco.
Thank you for having me. Hello, everybody.
So, what is the mission of Cortical.io, and what made you, or what prompted you, if you will, to start the company?
Yes, so our mission is in fact to make language computable in the very sense of the word. What we try to do is to get actually what is the human part in using language, namely in transferring understanding, sharing understanding of the world and of things. And nowadays, a lot of business is actually depending on understanding what someone writes or says in terms of language. And we are specializing in doing this very efficiently.
When looking at the evolution of natural language processing, how did it start? How did we approach this problem in the past?
Yeah, so we used, as very often in science, we start with quite naive approaches. We try to do a lot of acrobatics with the literal words. So we were parsing words, and when we then progressed, we started to count how often we see a certain word, and we tried to find out how important is it as a part of the message. And then we figured out one day that language has a certain number of statistical properties, and we started to do statistics, and by doing so, things improved. On the other hand, what we could see is that we were improving all the time, but we never came any near to what my, I don't know, 8-year-old son is actually showing as language capabilities. And so I got interested in finding more fundamental differences when working with language. And I mean, the only reference implementation for language we know is actually the human brain. And that was basically the reason why I tried to bring those two domains, the brain with its ability to understand the world and to communicate and to exchange information in a very smart way, to basically link this with the computer science side of things that tries to handle information in sort of structured, controlled environments. And very soon it became obvious that the current approach, which I would say is a brute force approach, so we were basically brought into the belief that if we just added more and faster computation, we could at some point come up with the capabilities of humans. Today, it's a situation where we have the best human brains, let's say Noam Chomsky or so, talking about language, uses about something like 15 watts. Yeah, I mean, it's not even a light bulb. On the other hand, the smartest and most refined systems use a couple of tens of thousands of watts and still are not wherever near to my 8-year-old son. So there has to be something that enables the brain to do this. And I mean, you could say it's something spiritual or so, but if you try to say this in terms of science, it has to be something that at some level needs to be able to be implemented also as a computational model. And interestingly, it's now about 10 years ago, I basically discovered the work of Jeff Hawkins. He's also known in the context of Numenta, and before that, the founder of Palm Computing, in the good old times when sort of the mobile world was still in the beginning. And he sort of turned out to become a brain scientist of his own approach. And he was doing a lot of interesting work in finding out what is the computational principle of the human neocortex. That's the part of the brain that actually does the thinking. He basically came up with a theory that explains how this works. And I just took that theory and tried to use it as a set of constraints to say, okay, within that sort of space that his theory offers, the sort of way of doing it the right way has to be there. Yeah? I mean, if I'm sure that that's the only possible way or space of finding a solution. It turned out that if I applied biological concepts, like, for example, the fact that every information in the brain has a very sparse binary representation, and I made this also to a constraint on the computer science side. And I then added the aspect, for example, that the brain learns about things as it processes it. So there is no separate training phase and usage phase, but it's one amalgamated sort of process. And again, I applied this to become a constraint on the demand of the algorithm. Suddenly, I ended up in a configuration like magic to me, because you know how it is. I mean, you figure out something new and then you ask yourself, but haven't there been like 300 people coming up with this? I mean, it's so obvious once you sort of discovered it. As a next step, because up to that point, it was only a theoretical sort of way of thinking, more a philosophical answer to the question. And we said, okay, let's try and build this. Luckily, we got some public applied research fund in 2011 that allowed us precisely to try and sort of build this for the first time. And although the project was supposed to run for a year, after half a year, it was clear, okay, that works even better than we would have anticipated. And from that moment on, we kept discovering a lot of aspects, and sort of a recurring pattern was actually that especially the hard problems in the old way of doing things became sort of side products. You did not even need to do that expressively. It was part of the whole process. Yeah? And so in the end, a very fundamental learning I had was we were all struggling about precision. You know, everybody was, okay, how precise is this new algorithm? And then we came up with pretty smart ways of measuring how precise it is and so on. And we, of course, had the idea that the more precise the system will get, the better it will do all sorts of jobs. Interestingly, what we have forgotten is that our magic key with the traditional approach was brute force. Yeah. So getting better means being even more brute force than the version before. And interestingly, we have achieved, or we have arrived at a level today where in principle we could generate any required precision. The only problem is that at some point a certain, let's say, higher precision would take 360,000 years to be computed. I mean, assuming that you have access to endless Amazon GPU-powered clusters of machines. Yeah, and the finding was, okay, all of that is not in fact about precision, but it's about efficiency. Because only if I'm really efficient, I can sort of scale to whatever precision I want. And if you look at this in even more detail, you will find out that the whole of evolution is in fact about efficiency. Because if you are efficient, you get more food for less effort, sort of, which increases your chances of surviving the next winter, okay? And that was a very fundamental sort of finding for me that was not expected at all when this all began. And today I see that in the wild, which is the business world, of course, that actually turned out to become more than true, because most of the of projects that are started by even large corporations and so to, for example, automate some processes that they have, that depend on understanding the content of an email or figuring out what a note to a document means and making different kinds of decisions. If you want to solve this in the real world, you will find that it's all about how efficiently can you do this. Because if in the end, every automatically processed documents costs you $12,533, a lot of potential customers will say, okay, I mean, it would be nice to have this, but that just doesn't make sense commercially. And so it's an unexpected pressure that comes up, I think, in the midst of this hype that, yes, we can model everything, we can use machine learning to solve every problem. Yes, it looks as if we can, but the limiting factor is not what we thought would be the precision of whatever algorithm we use, but it will be the efficiency. And that's where we are today.
What are the benefits to using a neuroscience-based approach in natural language processing?
Yeah, so in the end, it's much more efficient. So if you do statistics and you have a system that you want to describe by statistical means, and that system has a lot of situations where it doesn't behave linearly. It doesn't behave like the interpolation between two states, but it happens to have some extra special case. Yeah, and if it has a lot of special cases, then you have endless effort in sort of saying, okay, in principle, this system works like this, except for this situation or for that situation or for that situation. And then it might take you 20 years to come up with all the possible situations. Just take driving. Yeah, I mean, if the task would be to drive a car on a half-empty highway, we would have self-driving cars already 10 years ago. Yeah. The problem is that in the real world, there are so many special cases that it's very hard for a mathematical system that tries to work with a lot of data and the average of these data to find the right decision. Our brain is wired in a very different way. It only learns on special experiences. So the normal driving situation is a specific sort of situation that your brain learns, as well as this very exception when the deer was crossing the street. And each of them is using, let's say, one memory slot. And once you have had I don't know, 1,000 memory slots done, you already have a pretty realistic pattern of normal and not so normal situations. And so you only need a fraction of the training data that you would need if you would do a sort of, under quotes, dumb brute force approach, where you just say, I throw in as much data as I can, and by statistics, there will be enough special cases.
Sousa Webber, founder and CEO of Cortical.io. If somebody wants to connect with you, Sousa, what's the best way they can do that?
Best thing is over LinkedIn. I have an account that makes success easy. I'm happy to answer any questions.
Thanks for everything that you're doing, and thanks for joining us. And if you guys want to find more of my interviews, you can do that right here or go to tonyahall.net. Thanks for watching.